I'm sorry. Sorry. So we'll start the next sessions after your ears stop bleeding. Sorry about that. The next talk is from Damien Turci and David Evenstein, who are the founder of the Drexel chapter and the current president of the chapter. I'm really looking forward to hearing from them. This is the first time that we've met, although we've been working together for a couple of years. The Drexel folks first approached us at Icarus shortly after the 2013 Starship Congress, and we were actively seeking a way to try to get interstellar education and inspiration, into school. So they fell and they filled that gap really quite nicely. And they've been participating very actively in Icarus's projects over the last couple of years. They participate in Project Icarus and with Project Tintin. They've attended some conferences with us. So without further ado, Damien and David, if you would like to come up.
Good afternoon, everyone. My name is Damien Turci. I am the founder of Drexel's chapter of Icarus Interstellar. And the main reason behind the speech that the two of us are going to give today will be to discuss Project Zeus, which is Drexel's answer to Project Icarus. However, before I hand the stage over to David Evenstein, I always have trouble pronouncing his last name. Before I hand that over, I would like to take this opportunity to tell you my insights on the invaluable need for student involvement in the development of making a starship. Dr. Ixioulas, he wrote in 2012 a paper concerning Starflight Academy. And in this, he says that interstellar engineering education is the great motivation for change that will be needed so that we can reach for the stars, and in doing so, make the solar system our playground. But how can we do this reaching when there are so few of us? We need numbers, and I think one of the ways to do this is to create student chapters all over the world. Let students know that this is not science fiction, that this can be scientific reality if we work together on this, which is perhaps the greatest endeavor that the human race has ever set out to complete. So when you go home, in the audience and anyone watching at home, create a student chapter at the university that you were affiliated with. This will create knowledge, this will create passion, and most importantly, this will create numbers. How can we develop an interstellar spacecraft without bringing a whole generation of new people to become involved in our cause? Think about this. These students that you make chapters for will become the next round of professors, managers, and politicians. And then they will perhaps remember that club in school that had such a consuming desire for the survival of the human race that they will enact it into their classroom lectures, into their company policies, and into their legislation. So I am challenging you today to go and create a student chapter. Let's take Drexel as an example. We started 3 years ago. And in that time, we've done some pretty incredible things for not even having aerospace engineering offered at this school. The students involved in this chapter, they created a spacecraft, theoretically, a 70-page design report on a plasma jet magneto-inertial fusion propulsion. Just, wow, like, how did they do that? They're students that don't even know about aerospace engineering. Very few of them know about nuclear engineering. Also, we have a student who he just completed his freshman year, and for his summer, he worked on field emission electric propulsion. His name is Noah Alessi, and you will see his poster today about experimentally characterizing this. On less serious note of what the students have been involved with, there was one meeting where we wanted to explain general relativity without having to introduce tensor mathematics. So we got Play-Doh. And what we did with this Play-Doh was, for those who are unfamiliar, we were able to create space-time metrics. You know, fold the Play-Doh over, put a hole through it. Look, there's a wormhole going through space-time. And then the students broke out into groups and created their own exotic space-time metrics. Maybe there is an alternate solution other than the Alcubierre warp drive that will feasibly allow faster than light travel. So I want to show you this for the first time. If my pointer will work, there we go. So this is an animation of the plasma jet magneto-inertial fusion system for the Zeus spacecraft. It looks pretty cool, right? This is I just saw this the other day. It blew my mind. And the idea that we are going to do to expand with this is that we want to connect this animation to numerical solution to the governing equations for this fusion system that are calculated via Simulant. And then what we could do is change colors on this animation so that the technical audience watching could actually see changing magnitudes of physical parameters. So not only would this animation have a reason for the non-technical crowd to see it, because it looks cool and it explains the fundamental concept behind it, but also the technical crowd could see changing parameters and have some type of rationale behind this. And when we were creating this, we got the idea that we don't just need to do this for Icarus Interstellar. We could expand this beyond to any type of new engineering system and perhaps sell it in a contract. And then I had the idea that maybe we could give a percentage of this contract to Icarus Interstellar for birthing such a different type of look on things. Here's another type of animation of the plasma jet magneto-inertial fusion system. Pretty cool looking stuff. So anyway, I digress. Within 3 years, we went from 5 founding members to over 60. If we assume a constant growth rate, within 5 years, we will have approximately 100 members. Now imagine if 10 of you go out and create student chapters. Within 5 years, we will have 1,000 new members of Icarus Interstellar. We will have numbers. But for those watching at home and those in the audience, I want to take it a step further. Not 10, no. We need to do 50. 50, so that by 2020, we can have 5,000 student members. Imagine a Starship Congress with 5,000 student members. That would be absolutely crazy. And we could have competitions with these members to actually push forward this research that only a select few are working on right now across the world. And even though there are few of us right now, we are spread out throughout the world. Our leader is in Alaska. We have the leader of Project Icarus in London. well, the UK. We also have members in Australia, if I'm not mistaken, Florida. There's a few in South America as well. We could have student chapters showing up literally across the world. Just do it. So, with that, let's become the AIAA of interstellar engineers. Thank you.
So thank you, Damien, for that stellar introduction and this interstellar chapter. My name is David Everstein, and I'm the current president of Drexel Interstellar, and I have been since the spring. But I've actually been a member of this ambitious group since nearly day one. Now, I'd like to say straight away, the best part of working on this project Icarus was all of the very unique, very exciting knowledge that we gained from it. Finally, we students who were not aerospace majors, we are spread across a bunch of different disciplines. Finally, we students could tell our friends, listen, this is rocket science. This is what we're working on. And the quantity and quality of all we learned while designing our student spaceship was mind-blowing. And it's very valuable to us and something that we'll hold on to for a long time. So without further ado, I'd like to unravel for all of you our Project Zeus and maybe share some of that learning with you. So I'll begin with PJMIF. Damien mentioned it a few times. Plasma jet magneto-inertial fusion. Sounds like a bunch of very techno-babbly words strung together, but that's the mouthful that was thrown at us rocket rookies as we started this project. That's the field of physics few of us had ever ventured into. And that's the method with which we had to carry a 1,000-ton craft to Alpha Centauri, 4 light years away, in less than 100 years. That was an intense challenge. So I'm going to go through it now and hopefully give everyone a close look at its inner workings. And I'll begin with plasma. Plasma jet magneto-inertial fusion. So plasma. Why plasma? Plasma has been studied since the early 50s as a subject for nuclear fusion. And a nuclear fusion engine is one of the requirements of Project Icarus. Now, what are we going to do with said plasma? We're not blowing it up using chemical reactions as a typical rocket would. We're not peeling off electrons for ion propulsion. No, we have to give this so much energy that it goes through nuclear fusion. We have to be bigger, we have to be better, we have to be more powerful than any engine ever developed before. All those are already developed technologies, too slow for us. We need to think big. So, plasma. For parameters I'll mention later, we chose the plasma deuterium, which is a hydrogen isotope with a proton and neutron. Now, what do we need to do with this deuterium? First step, we need to get it in the engine. Our engine has 2 theta pinches located on opposite sides of this nozzle that you see here. Now, what do these theta pinches do? They take the plasma, they confine it using a very clever magnetic field in a configuration known as a spheromag. And it shoots out 2 of these plasmas from opposite sides. They form, mingle at the middle, and finally merge into a plasma. And they sit there peacefully, right up until they're promptly shot. This brings me to the jet portion of plasma jet magneto-inertial fusion. Project Daedalus, our precursor, which has been mentioned already, employed lasers in order to energize this plasma target and bring it to nuclear fusion. But the PJMIF concept decides instead, why use lasers when you can throw even more high-energy plasma into the mix, adding to your reaction mass for the fusion, and donating that energy to the target. So jets. Essentially, a railgun that fires a very high-energy magnetically accelerated plasma. Now, studies have been done on this before, which used everything from 4 to 48 such jets, but 48 jets, that might be enough for an evening stroll to the moon, but not to Alpha Centauri. So we had to think bigger. We had to scale it up. 150 plasma jet railguns. That showed much more satisfactory numbers, and that would have been capable of carrying us to Alpha Centauri. So what's next? Plasma jet magneto-inertial. Magneto-inertial is what we need to cover. Now, the magneto-inertial part is very interesting. That is what actually incites the fusion and gives the energy to the plasma target we discussed. These 150 jets, when converging on our plasma target, donate not only their inertial energy as they're traveling at Mach speeds and impacting this from all sides, creating a spherical pressurizer known as a liner, but they also give it a bunch of magnetic force. Now that magnetic force, what it does is it takes the spheromac that we have and converts it to field reverse configuration. But I'll keep it simple for the sake of this speech. Basically, it propagates magnetic shock waves all throughout the target, thus giving it additional energy. Now, the energy that this system provides is just enough to activate deuterium into fusion. Not just enough, it's actually ample energy, megajoules of energy donated by these jets to the plasma target via magneto-inertial confinement. So that's when the kaboom happens. That's when fusion occurs. So fusion, there you go, the last word, the final piece of the puzzle in plasma jet magneto-inertial fusion. Now this reaction happens inside of our nozzle, as you saw in the simulation a few slides ago. And you have a nuclear fusion reaction occurring inside of your spacecraft. So how do you get that out? How do you get it to not directly impact your spaceship? Well, that's my favorite part of the design. You notice these copper-colored coils, well, they are copper, or would be, describing the profile of the nozzle. Now, those generate a donut-shaped magnetic field all throughout it. And when the 1.5 septillion individual fusion reactions occur inside of our engine, particles of energies averaging 3.5 mega electron volts are shot in all directions. And once these come close to those coils, come close inside of that magnetic field, the magnetic field is actually deflected into a parabolic shape, a shape that is essentially the same as our nozzle, pretty much parallel to it. And because of this contour, all of these charged particles are deflected straight outwards along our desired axis of motion. And from that we get thrust. Now, thrust values from this craft range from 0.5 to 15 meganewtons. It's not the biggest, most powerful engine that exists, but our ISP value has shown numbers that were incredibly high, ranging in the area of 1.5 million seconds. That means that we can make it to Alpha Centauri with only 4.5 to 6 years burn time. That means we only have to pack as much fuel as we need to burn for 6 years straight. Now, of course, that's a lot of time, but 3 years fire accelerating there and 3 years back isn't actually that bad, and our engine can more than handle it. And the ISP actually gives us fuel mass of only 78% of the ship has to be fuel, which for interstellar probes of this size, not that bad, not too shabby. So now that we have PJMIF, plasma jet magneto-inertial fusion, it's no longer techno-valuable, right? And you have your foundation for an interstellar probe. You have your ticket to Alpha Centauri 4 light years away. Now that we have that, I'd like to look at other inventive aspects of our design brought to us by our members. Now, those of you who are unusually keen might have noticed that our magnetic gizmos, they don't deal with the neutrons coming out of the reaction. Those have energies of around 14.1 mega electron volts, and they're shooting everywhere, and there's nothing to deflect them. There's only the actual physical ship to stop them. And if we tried absorbing that much energy from a fusion reaction, we'd be flying an interstellar puddle in a matter of minutes. So we have two systems in place to combat this, designed by members of our organization. The first, a tritium breeding section. A tritium breeding, what is that? When these neutrons collide with isotopes of lithium contained in a tank, going throughout the plumbing of the nozzle and above it to protect the rest of the craft, when those neutrons collide with lithium-6 isotopes, they produce, among a few other byproducts, a tritium plasma as well as a neutron. Now, what is this tritium? Tritium is another, similar to deuterium, except with one extra neutron, plasma of hydrogen. But throwing that into our fuel, throwing that into our engine, would reduce the energy requirements of our fusion. That's very beneficial to us. We like that. So we're going to put lithium-6 shielding around it. Now, lithium-6, the reaction also produces a neutron of lower energy. That neutron, coincidentally, when reacting with lithium-7, produces even more tritium, plus for us. So we have this tritium, which is actively being produced by our fusion reactions, which we can recycle into the fuel. And now, since tritium is unstable, unlike deuterium, it only has a 13-year half-life. Due to the active production, we don't have to worry about that. So it's just an added bonus, and it lowers the energy of incoming neutrons. Now, the rest of the neutrons are completely stopped by a bismuth-loaded polyethylene shield. Calculations have shown that this shield does not need to be especially thick or massive to protect the rest of the craft after the neutrons have been filtered through lithium. So our fuel tanks, our data modules, our payload, all of that is safe now due to the neutron shielding that we provide. The rest of the heat accumulated by that can be filtered out and radiated by conventional means. Now, when we unveiled our design for the first time at the Atlanta conference, I distinctly remember the attendees there looked at the conical bell and immediately wrinkled their noses and had this general expression of disgust. Aerodynamics in space. But of course, that's not the purpose of our design. The conical, well, it was actually because we have members ranging from such a wide field of disciplines that we happen to have an armored vehicle enthusiast among us. And he suggested an angled shield for the craft. Now, why do we need a shield in front of the craft in the first place? For those of you who are already done the math, 4 light years away, 100 years, that means you have to travel at 4% the speed of light, which is fast. Anything that's in our way, anything that's even a milligram in mass, a dust particle, for example, would shatter our ship. It would rip straight through it if we did not have the proper protection. It would render it useless. So we need to have something to at least somehow prevent this sort of catastrophic effect. So, angled shielding. A bumper at the front of the ship, which was our original concept, would have to be fairly thick and very massive in order to save us from this. But if we get a conical shield, which has the same mass and thickness for a similar radius as just a plain flat bumper, can actually deflect a great degree of a particle's energy as it collides with our craft. Now, our materials members and those who did research on it developed Kevlar and aluminum foam material for this. Aluminum foam because after an initial impact, which would be deflected, our ship would survive. Actually, with this design, it survives impacts of up to 1 gram of mass at 4% the speed of light, which is, wow, you're not going to find bigger than that in interstellar space. We hope, at least. We don't know for sure. If we do, not know what to do about that. If we hit UFOs on the way, we'll have to leave a note that says we apologize. So this aluminum foam at the top actually has small regenerative properties where it fills itself in at the crater rim, which is good because we need that smooth outer layer in order for that deflection of energy to occur. So moving on, we also have, I'd like to talk about our mission when we reach Alpha Centauri. So we have this huge conical shield. We slow down at Alpha Centauri, and what do we do with it? We don't need it anymore. It's not shielding us from anything. So we proposed to open it up. Similar to a flower blooming, it would fold on hinges into petals. Now, that opened our eyes to a lot of possibilities. You could put a lot of things in the shield of that design. For example, you could have solar panels lining the inside of it, and then point it at the suns of the Alpha Centauri system and charge up from that, Alpha Centauri specifically, in this case. And alternatively, you could spread a spider web, whether printed or pre-packed, a mesh that goes between the petals. And once you fold it up, you effectively have a communications receiver. Point that at Earth, and you can receive messages, and you can send from our communication system. Now, additionally, you see here these buoys on tethers. Those are what we refer to as sensor buoys. As soon as that shield is removed, as soon as we get to Alpha Centauri, our ship begins a roll. This roll unfurls these buoys, which take measurements of the system. They have a wide array of scientific equipment for taking planetary analysis, calculating distances between local objects, and cameras for transmitting HD feeds back to our home planet, so that people here in 100 years can view what's going on at Alpha Centauri for themselves. Of course, by that time, hopefully they'll already be planning their trip to go there, but we can send postcards. So, you have PJMIF, you have our Zeus spacecraft. This was all designed by simply a relatively small team of members all working together very studiously, all showing tremendous amounts of effort in developing this craft. So I'd like for you to imagine what would happen if we had these 5,000 members of interstellar chapters around the world. We could have people designing starships, interstellar probes, satellites, CubeSats, warp drives, even colony ships to send between the stars. What we want is for people to look at this presentation, students in particular, and see what the possibilities are. And maybe we challenge them to do better than us. We challenge them to do a ship that can do it in 50 years or in 25 years, or a ship that can carry humans there. We want students to zoom out. We want students to build a starship. Thank you very much.
You know, it always impresses me how far they've come in such a short time. And yeah, I just wanted to thank you guys. You're doing a really fantastic job. Everyone is really very, very proud of you, and everyone else in your chapter also. Next up, we have Bruno. Are you here, Bruno? There you are. Just grab your bio here. And Bruno is a French engineer who studied first agricultural and in the food industry before branching out into computer science. Today, computer science teacher at Tiananmen State University. Since his childhood, he's been truly passionate with sciences and space. And for the last 10 years, he's been involved in devising a strategy for overall interstellar travel. He's a great proponent for change and in large scales of approach, more than just a crew, a space nation, more than just a spacecraft, but an interstellar arc. Bruno?
Thank you. Yes.
This one.
So what you see in the screen is the interstellar arc. It's quite big, 10 kilometers long, 10 kilometers large. Okay, for the hollow cylinder here, full of atmosphere, of course. But okay, it's a world ship, and about the reason to build a world ship, we will speak it about during the hackathon, I think. But for this speech, I will speak about the bow, this mass. Okay, it is mainly ice, and we'll see why. The mass of the overall structure is about 400 gigaton, and the mass of the payload is only 20 gigaton. So that I want to show is why we need so many fuel at the bow, and a fuel which is not energetic fuel. It's only water. Okay, and this configuration, more than 95% of the whole vessel is water. Just a postulate for our work. No breakthrough, that is to say, of course, we need a breakthrough for fusion. If we have not fusion, nothing is possible. But okay, we say that to go from, to reach a distance d, we need to accelerate mass to a velocity v, under c, of course, and decelerate. That take an energy mv square, and the time is the relationship between energy and time is this one, and there is no way to do. There is no another way. Okay, that's our assumption. And for us, just to say it, this is the best explanation of the Fermi's paradox. Second postulate, it's not no say. Of course, it's physically possible, but we consider that light sail, photon sail, are solution only for light payload. Because if not, for a manned for an interstellar arc, we need a sail of the diameter of the Earth itself. So it is a vessel driven by mass ejection. So the mass ejection is, to calculate the mass ejection, you use the Tsiolkovsky equation. That is to say, the mass ratio need to increase the velocity from an initial velocity to a final velocity is there is two parts in the right part. The first part is u, the exhaust velocity. That is to say, the relationship between the dv and u is linear. That is great. And the right part is the relationship between the mass ratio and the dv is exponential. I explain this because that explains why, for all the astronautical context, in the current astronautical context, mass is the enemy because of this exponential relationship. But there is a little problem, which is the energy efficiency problem. If u is much greater than v, all the kinetic energy goes into the beam, into the gas, not in the payload. That's a problem. The first solution is optimize u. That is to say, u remain constant, but we give it a value which is a constant for the acceleration stage, which is 0.6275. Okay, this is the first way, and we can do better by varying u. That is to say, if we set u equal minus v, then the the energy efficiency is 1. So you can do better. In this case, why it's 1? Because if U equal minus V, in the referential of the departure, the gas are at rest. That is to say, all the kinetic energy go into the payload and not in the gas. Yes? It's clear for everybody? In this case, this is not the Tsiolkovsky equation, because Tsiolkovsky equation is for U constant. So U disappear, and the final velocity is equal to the initial velocity magnified by the mass ratio. So in this case, the relationship between the velocity and the mass ratio is linear. It's great. But there is a little problem. That is because it's the depend of the initial velocity. If Vi is 0, there is a singularity, and the mass ratio tend to infinity. That's a problem. So we need a trade-off, and we will stage the acceleration. A first stage with U constant. So let's introduce V1 is the intermediate velocity, and we introduce R, a parameter. R is V1 equal R times Vmax. Vmax is the maximum of the velocity of the journey. R between 0 and 1. So in the first stage, R1, U equal, we optimize U by the first way. So you give to K1 the value of 0.6275. And when the vessel reach this velocity V1, the second stage begin, and U equal minus V, variable. Okay? This is the two first stage. There is a third stage, which is deceleration, because we want to finish the journey at speed 0, of course, because it's a managed travel. But sadly, in this stage, during deceleration, V and U point to the same direction, so we can't optimize by varying U. So we optimize U by the first way, giving to U the value K3 times Vmax. K3 is not equal to K1, we will see. So this is the third stage, and we need a stage, I name it ballistic stage, engine off, of course, because we want to travel at the maximum velocity as long as it's possible. There is, okay, a little problem here. So there is 4 phases, R1, R2, B, R3. In this case, the overall propulsive efficiency is given by this formula, which is a function of the 3 parameters, R, K1, K3, okay? The overall efficiency is the ratio of the kinetic energy taken by the payload, mv squared, and the overall energy expanded during the travel. Okay, this is a study of the function of the efficiency with the three variables. So we see first when R equals 0, that is to say, we begin by varying U. In this case, the mass ratio is infinity, so it's a singularity. And in this case, the efficiency is 1 in 2.04. This is a maximum. We can do better. It's not 1 because there is a deceleration phase. And the minimum is when R equal 1. That is to say, there is no stage with U varying. And we can see that for all the value of R, K1 have always the same value. So it's not a free parameter. And K3 is in linear dependence of R. That is to say, it's not a free parameter too. The only free parameter is R. But R is not is not very important. What is important is the mass ratio. So here we draw the curve of the energy efficiency to the mass ratio. So we can see that when R equal 1, there is no optimization by varying U. The mass ratio is 9, about 9. And the energy saved is 0%. And we can go to, if the mass ratio is infinity, the energy saved is 20%. So let's choose an intermediate value because we can't have a mass ratio infinite. So let's choose 20, and we save 10% energy. And this is the velocity curve. An important point is that we work at constant power. Okay, we have engine, and we expand the power of the engine are always the same, except during the stage B, of course. In this case, we can see that we are a first value of K, which is 0.63. Okay, so we eject the gas at this velocity, and the velocity of the vessel increase like this. When reaching 0.5 Vmax, U become variable, minus V, and the increase of the velocity is linear. Then we travel at constant velocity, and then we brake. We decelerate. Just to see what, okay, it need by this way we need a huge volume of water. So an idea to collect water, because in the current astronautical context, mass is the enemy, but not now. Now it's the energy is the real problem. We can collect huge mass of water, for example, like this. We choose an acid asteroid, a Trojan-like. I think you know what is Trojan. It's an asteroid in the Lagrange point of Jupiter. Yes. And why we choose this one? Because it's iced asteroid. Because the asteroid in the asteroid belt are silicate or metal and few waters. So it's mainly water, okay. the mantle of the asteroid is waters and CO2 and CH4 and NH3, etc. And silicate, metal, salts. Okay, let's imagine that we inject steam in the mantle of the asteroid, and we put the arc in a geostationary orbit for a radius of the asteroid of 15 kilometers and a mass of 10 power 16 kilogram, and a period of 10 days. Okay, the geostationary orbit is about 100 kilometers. So we have a space pipeline. It's not a space elevator. It's a space pipeline. It's much easy to build because it's only 100 kilometers and the pressure is not so high, 10 bars. Okay, and to build the arc in a century, we need it's an assessment a flow rate of 10 tons by second. This is the arc. Okay, you can see the dimensions to have an idea, and it's a living structure. The other, okay, I couldn't develop all the arc, but the idea is to use the light atom of the solar system, CHON, to build a living structure. That is to say, the wall are vegetal fiber and waters, an ocean, and the fuel shield of an idea. And I will finish on this. It is the fourth stages of the journey, with the assessment of the value, the power. We take a power 10 petawatt, and the value of the velocity. The value Q is the flow rate. So we can see that we consume 84% during the first stage because the U is low, and we need a great flow rate. The thrust is about varying from 2.4 megaton to 0.4 megaton during the deceleration. And the acceleration is about a few kilometers by second by years. Okay, I think I will finish it at this point because the rest is for the hackathon, I think.
Sure. Do we have any questions for our speaker? Actually, I have a question.
Yes.
So I would like a summary of the mission. So you have a breeding, like a nice ice breeding in a treatment stage, and then it goes into the various stages. Are you talking about the efficiency of the engine, or
yes, the efficiency
instead of stages you have
the efficiency only of the considering the efficiency is only considering the U and dV. Yes, it's your question.
Yeah.
The efficiency of the engines themselves, we can say now
Yeah,
of course.
thank you. Thank you very much. Next up, we have Lucas Schrenk, who is a member of the sorry, give me a sec. Should have your presentation on here.
Some stuff with Icarus.
Which one are you doing now?
Icarus. And I need das little pointy thing.
If I may introduce Lucas to you. Lucas Schrenk is a master's student at the Technical University of Munich, currently working on his master's thesis at MIT within the Strategic Engineering Research Group. He's one of the team leaders of the Interstellar Spaceflight Research Group within the WARR, the Student Scientific Research Group for Spaceflight and Rocketry in Munich. The team is working on interstellar fusion propulsion as part of Project Icarus and participated and won the Project Dragonfly design competition, which was hosted by the Initiative for Interstellar Studies, which is an interstellar laser sail propulsion design team. The team over at Munich was very similar to the chapter, actually. So they were based at the University of Munich. They had 4 or 5 team members. They had an interstellar working group. And they came and they joined Icarus Interstellar early on, and have participated really meaningfully since. I have a lot of respect for the team and for their leader Andreas Hein, and Lucas is done a really fascinating work. I'm really looking forward to your talk.
Thank you, Andreas. So first of all, thank you that I have the possibility to be here. It's great and amazing, my first Starship Congress, and I hope there will be more following. What you see here, that was our team. So we're not that lucky and had a constant growth rate like the Drexel chapter. We are now basically just 2 people still working on the design. And it's difficult to get new students into interstellar spacecraft theoretical design when they design rockets and CubeSats next door at the same organization. So that's one thing we have to address in the next couple of months, I guess. And what I'll talk about is shortly about Project Icarus, because our project leader, Rob Sweeney, told me that I'm the most senior member of Project Icarus presenting at Starship Congress, which I have the honor to do this introduction, and then talk about our ghost design, about the spacecraft propulsion mainly, and the important part of the spacecraft bus. Then make a conclusion, which may not be as positive as the Drexel results are, but it's a result, and that's what science is about, I guess. So, as you already heard, we update to Project Daedalus, see what after 30 years, 40 years can be done with the new knowledge in engineering. So, they started in 2009 with primary research and trade analysis, and in 2013 we decided to have a design competition. That's when the Munich team entered. That was to have a fusion-propelled Starship that brings 150-ton payload to Alpha Centauri. Yeah. Sorry. I'm a bit nervous, sorry. It's my first really large presentation. I hope we'll get better throughout the presentation and for the next presentation. So what I want to say is with the design competition, the real concept design started where we now started to compete against each other, and each team did their own design, which is basically Firefly. It's a set-pinch fusion-propelled Starship designed by Robert Freeland. If you have any questions about that, you can ask him. We have Starship Resolution, which is ICF with helium-3. That's Kelvin Long mainly. Then we had a UDD that uses ultradense deuterium, a really dense form of metallic deuterium, and the performance would have been great, but we said we're not sure about the scientific results yet, so let's skip that for now.
Then we have the Zeus team, the newest team in our family of designs. You heard about that. And then we have our Ghost team, which is a neutron pump laser, fast definition, deuterium inertial confinement fusion. It's a long title, so I'll now elaborate what that is. Our propulsion system architecture is we use for acceleration fusion propulsion only. Our ISP is not as high as Drexel or any other teams. I will talk about that, why. We have 360,000 seconds and a thrust of 55 meganewtons. Then for deceleration, we use a combination of a magnetic sail and this fusion engine. But first of all, what is inertial confinement fusion? We use lasers to compress the pellet, like here. And then we have the fast ignition. That is one single laser pulse that should ignite the core and start the fusion process. Our pellet is mainly deuterium. That was one of the competition requirements, but we added a deuterium-tritium core to lower the ignition energy of the pellet. So basically, we optimized the size of the pellet and the compression ratios we will talk later about. But right now, for our design, we have 84-gram pellet, roughly 10 centimeters in diameter, and a high frequency of 150 hertz, so 150 fusions per second of these, that equals a mass flow of 2.6 kilograms per second with that system. The compression rate has to be high to achieve high burn-up compression of the pellet and not lose deuterium to just going out through the nozzle. And that requires us to have high laser energies, and with the laser efficiency, even higher power requirements. So how are we going to do that? We have this neutron pump laser system where we basically use the neutrons from the fusion, which are a lot for deuterium, and have this chamber around where we have uranium oxide and neon. And in this chamber, the neutrons from the fusion, they fission the uranium oxide, and the fission products, they excite the neon gas, and these laser flashes are collected and then by light pipes and going into the amplifier, which is then used for the fusion. Go to the next part. We did some calculations. So at first we just set basic assumptions, how much neutrons are produced in the fusion, the normal reaction. But then we said, okay, we have to rework our design. We have to make it more thorough analysis, and came to the conclusion that a lot of neutrons are already shielded inside the pellet by the deuterium that is not fused in the outer parts. So our numbers of neutrons and the energy got reduced. We had to increase the size for all the other systems that required the neutrons. And that, leads us to the neutron powers. All these diagrams you see are integrated in a MATLAB simulation that gives us, with a trait space analysis, an optimal design in the end. For our specific impulse, we use the Taylor's analysis. Is applied it to our ratio and a higher ISP. So we thought that by the additional system an optimum low ISP, but a drive unique. Here our as for design, we have a one coil system, an efficiency of 75%, and so the one coil produces the magnetic field, and the diverter magnet at the end, it's not shown here, closes this magnetic field so that a lot of the plasma is directed into thrust direction where we want to have it. Another problem we had is that the coils are so close to the fusion that they're bombarded by neutrons, so they have really massive neutron shield. For deceleration, I said we will go to use a magnetic sail. that is basically a superconducting loop that is producing a magnetic field, which is interacting with the interstellar plasma and thereby producing a deceleration force. But as I said, interstellar plasma, that's highly depending on that, and there's just assumptions about that, and it's not very dense. So we need large radius. It weighs about 1,000 tons and high current. But we decreased the size of that. We had really not feasible sizes, but that was one of the steps we took, just make everything more feasible. So that's how our ship looks like. You see the small spacecraft and then the large magnetic sail. Yeah, if the question arises, that's not deployed during acceleration, so it just will be deployed shortly before it decelerates the spacecraft. So our spacecraft, you can see here, it's roughly 1.2 kilometers long with a dust shield in front. We don't have this pointy design. That's basically ablative shield. Impact will just evaporate the shield over time. Behind that, the payload section. Here, the deuterium tanks and the pellet manufacturing with thermal system to keep on cryogenic temperatures. Then we have here power system and tritium storage. Tritium decays, produces heat, so we have to get rid of that. The whole thing is attached to a carbon nanotube structure, a very thin one. And here is the propulsion system with their large radiators due to neutrons and X-rays that produce heat and we have to get rid of. Our configuration, just to explain why we chose it. So here, the fusion, we said, okay, let's get everything that is important as far away from the fusion as possible and use a small shield to not have too much heat input and then protect the rest of the ship. That was the main idea behind that. So the whole shield mass is very low compared to the overall ship mass, and that's why we have the longer ship. As material, it's a polyethylene doped with some materials that we assume based on literature we could find on shielding material. But one thing that is very important, just wanted to mention it here, the total neutron power we get radiated isotropically is 5,110 gigawatts. So Interstellar, we learned that's for interstellar spaceflight, gigawatts and something like this is not a large number, but if you calculate then in mass, then it gets heavy. So we had to add additional shielding here to protect the structural elements. So that's that's the diverter magnet, and that's the large coil. So the uranium oxide chamber is not shown here, just that we could see the actual shield. And this configuration leads to 620 gigawatts of heat that we had to get rid of. We did that first. In the first iteration, we looked at liquid droplet radiators. I don't know if you're familiar with that. You use metal droplets, shoot them into space, and let them cool down, then collect them again. The problem with that is there were large surfaces and a lot of mass loss due to evaporation. So we got back and developed the phase change radiators in collaboration with the Firefly team. And now have lithium coolant with carbon-carbon fins that possible to get us a specific weight of 80 kilowatts per kilogram. The radiators you see here are on the ship, roughly 400 meters long and on both sides 1 kilometer wide and weigh 8,000 tons. That's a lot, but we have to get rid of the heat somewhere, and that was the best way to do it. Another important bus element I want to talk about is communication system. For interstellar communication, we have high losses, so you need a lot of high gain, which is either a large antenna or your power system. Right now, there's a new power system under development within Project Icarus that we may use for all the designs, which uses large antennas and to transfer a data rate of 20 gigabits per second. That's the idea behind that. We thought within our GHOST design, we have the magnetic sail, so we can use the base structure of the magnetic sail as a base structure for the communication system. We will look into that and for the final report, hopefully finish it. Additional bus systems we had looked at are navigation, onboard data handling, all the thermal control system for keeping the deuterium stored. Pellet manufacturing is also important. We had this deuterium tritium core, and when you have the tritium inside, and it would just melt the pellets over time, and the tritium decays. So the pellets have to be pre-manufactured before they are sent into the fusion chamber. And then the pellet injection. For that, we use the Daedalus approach of just a magnetic gun, because all the other technologies would have been too heavy or would have required propellant. So, told you what the technologies were we used, how we did it. We had a lot of tweaking to do to get the ISP higher and to get our mission time down. So we're basically accelerating only for 2.5 years. That is good, because that limits the exposure of the structure to neutrons and all the thermal loads. We reach a velocity of 2.3% of the light speed. That already will tell you the result of our mission time, which is not 100 years. And then we're cruising for 73.5 years, decelerate for 110 years, until we finally reach with fusion. The last bit is done with fusion, orbital velocities around Alpha Centauri. And the total duration is 186 years. So slightly above the requirement. Our results showed we could decrease it by at least 10 or 20 years, but that would mean twice or even more propellant. And like you see here, we're already at 1.5 million tons, roughly, 450-ton payload, mainly because of the mass of the propulsion system. The initial mass of the uranium oxide that we have to take with us is 270,000 tons, and it's used up over time, but the initial mass is really high. So that leads to a fraction of 0.01%, which, yeah, I wouldn't send a ship with that kind of payload fraction. That's not worth it. So we should go with a different design. That's my result. It's not positive, but I guess, yeah, we have to deal with it. So our conclusion is that the fast ignition technology that we got in the competition to what we were asked to analyze in the competition doesn't make it in 100 years, and that our neutron energy recovery system is too heavy. So possible solutions are we use a different propulsion system, use our spacecraft bus and add another propulsion system and start from all over again, or we could use this massive propulsion system. So we looked at MHD generators to get energy back from the exhaust stream, but that lowers your ISP even more. And first analysis showed that that is too heavy. So there is something where we are now searching to find a better way of recovering the energy required for compression. And then I will draw the final conclusion. So Project Icarus will come to an end soon by publishing everything that we did, summarizing everything and get all the designs ready. And we at Munich, our team, so persons, will try to get the best design possible until that. Thank you very much for your attention. Any questions? Please, Robert.
Yeah, one of the most innovative things about your design was that whole neutron recapture.
It was, yes.
Pumping thing, and I was wondering if you ever considered something other than uranium for that, or just something lighter.
I cannot really answer that because that's propulsion. I'm the project leader and the system bus designer, not the propulsion. But I think. I cannot tell you the answer right now, but I will get in touch with my propulsion guy and yeah, we'll tell you that. Yes?
How would you restart the lasers without already having the stream of neutrons coming in?
We thought about that. So what we could do is have at least some capacitors for the first charge them, use the lasers, ignite the first pellet, and then use the neutrons all over again, or ignite a neutron bomb or something that was the more science fiction stuff. Maybe we weren't sure if we should do that, but yeah, we thought about that, and it's difficult. That's true. That was also some kind of problem for risk analysis. What happens if you miss one pellet at some point? during the acceleration period, then you have a problem, because then you will just break the whole cycle and have to start all over again. Further questions?
All right, thank you. Thank you very much. So we'll give you a few directions for lunch. Now we'll break for an hour. We have some of Philadelphia's best food trucks have come by to visit us. They'll be outside in the front. And there's a really nice area upstairs that's open. It's such a beautiful day outside that we can go and eat upstairs. It's just outside these steps going up, and the atrium, where we're going to do the hackathon, is right beside. So we can start migrating over there. And we'll give about an hour before we return for the third block of talks. Let's do it now. Hello, everyone. Good afternoon. I hope you had a nice lunch. We'll start our afternoon session. So our keynote for the afternoon is Mr. Zach Fayes, who joined Icarus, who joined us, actually, we met him at Starship Congress 2013. And he was one of those members who stuck with us in our memory. You know, he wanted to participate in any way. He had a lot of energy, so much energy. I was like, well, I don't know what I'm going to do with this guy. He's gonna, he really wants to participate. He wants it all. And I remember reflecting, a couple of months later, there was this little lapse where we didn't interact. And I was like, I need someone to come in to this organization and I just breathe in some energy. Like, you don't know this. And to breathe in some energy. And I was like, I know. We're gonna spin up Zach's project. So not even 2 years have passed since then. Zach became a project lead, built a very successful team around him in Toronto in Canada. Some of his team members are here. Really excited to see you guys here also. And the project that they're working on is a problem that we had for a very long time, which is how to plot mission trajectories for the spacecraft that we were building. And the problem it's pretty intense, because we are an international group, and most of the good mission planning software are covered by ITAR restrictions, and they're not easily attainable. But as a project, it was fascinating. That what Zach wanted to do was to build it from the ground up, and that's what we're going to hear. He's going to talk to us about today. This is Zach Fayes and Project Voyager. Please welcome me and welcoming Zach Fayes.
Hello, everybody. Is everybody all well fed and not too snappy to do a meeting? Well, thank you very much for the very lovely introduction. My name is Zach Fayes, and I'm an electrical engineer from Canada, and I have always wanted to be an astronaut. That is what it really comes down to. That is what has effectively driven me to do pretty much every major decision I've made in my life. That's why I studied engineering. That's why I came out of Starship Congress in 2013, sorry, now it's 2015. And why I wanted to get involved with Icarus when I had the opportunity. You see, a long time ago, in Toronto, my father got me a copy of Star Wars. And I said, this is phenomenal. I would love to be that person. I would love to be that person exploring new worlds, seeing amazing things. And I'm not going to mention the Force because this is a science conference. But long story short, I wanted to be that person who would go out and explore and learn these amazing things, but I had no idea how to get there. And this is, as it turns out, as I grew and studied engineering and I studied more and more science, and as I learned more about the industry, I found out that this was the problem everywhere. I mean, you're here today almost certainly because you're interested in space travel, and you are interested in understanding how we can make our amazing dreams of interstellar space flight, deep space flight, even flying to the moon regularly a reality, and you want to make that happen. In a much simpler case, an astronaut, which is hilariously not simple, the question still arises, how do you get there? How does that become your profession? I mean, in the entire history of our species, just over 100 people have ever had that job. There is no way to do it. There's no program in school where you study astronautics for 5 years, you go get a master's in astronautics, you get a PhD in island and space ecology, and then you go work in the ISS for a few years. That isn't how it works. There is no route to that. And if that sounds hard, look at what we're trying to tackle today as an organization. We're trying to tackle interstellar spaceflight. There is not a single machine we've ever built that has traveled to another star system, nevertheless a person. So the problem that I see myself facing in terms of going where I want in my career is nothing by comparison to the problems we face as an industry in terms of making these amazing things become a reality. And the question naturally has to become, how do we realize these incredible dreams? How do we realize these amazing ideas we have? And frankly, it comes down to, how do we get there? How do we make these things happen? Now, this question is effectively going to be the basis of my talk, and I'm going to describe Project Voyager in the scope of an answer to this question. And I think I have come up with an answer to sort of this what I think is the most pressing question in the space industry today. And I'd like to explain that a little bit. You see, I have come to the conclusion that, at least through my relatively short time working in the space industry, I've come to the conclusion that the biggest problem is one of focus in the space industry. And amongst all of us who are not only working in it, but enthusiastic about it, artists, people of different professions who are enthusiastic about the space industry, all have a similar hang-up. And that hang-up, quite simply, is we look at these amazing concepts. We look at concepts like what the EagleWorks team is working with at NASA, the warp drive concepts. We think of interstellar spaceflight, and we see this amazing and nigh unattainable thing, which we'd like to make a reality, and we work in many ways to say, okay, if we had technology A, we would do it. If we had technology B, we could solve this other problem. But we don't have those technologies. And it's very easy as a young professional or as a student, or even as an experienced professional, to not be able to get past that. It is working, it's just a black screen. So it's very difficult to not get hung up on in some ways, the possibilities within our lifetime of seeing certain things become real, seeing a warp ship that travels with hundreds of people on board to another star system become real. That's hard, and I think it really comes down to understanding, and not only understanding, but really celebrating each step along the way, each incremental little step, which brings me to really what this talk's solution comes to, the idea that incremental tools and the development of tools begets the development of more tools and more technologies. And focusing and celebrating each of these little steps along the way is how we tackle these problems and how we keep people really invested and believing that we can individually contribute to interstellar spaceflight. Even if it's 100 years away, everything you do today, even as a student, can contribute. So again, we have to understand what problems we're dealing with to break it down. Dr. Armstrong this morning mentioned that sometimes we have a problem of focusing too deep as scientists or engineers. I tend to agree, but based on the fact that I'm an engineer, this is my training, I like to break problems down. So let's look at the different problems of spaceflight and better understand how we can break it down, how we can get rid of this problem of only focusing on the top level successes and bring it down to something where each success makes a difference. The first problem is distance. Frankly, the nearest star to us is over 4 light years away. That's really far. If the sentence 4 light years away doesn't already make you shake at how impossibly far that is, it's very difficult to explain. Now imagine trying to explain that to a school child in a meaningful way. It's difficult. It's almost impossible to convince them that light travels faster than you could possibly understand, and do that for 4 years and you might see another star. That's hard. It's a hard thing to grasp. Another problem is propulsion. Once we have distance to deal with, we have propulsion to deal with. How do we get that far? How do we get that far quickly? How do we get that far with that much mass? How do we get off the planet we started on? So if we start on the planet, these are all problems we need to solve. There's the problem of navigation. There's a problem with mission planning and figuring out how to get there. Even if you have all of this fuel, even if you have this amazing ship using technology that we don't know about yet, how do you get there? How do you figure out how to go? And lastly, there's a problem in education, which is very similar to what I'm talking about today, the focus on what counts as success in the industry. The focus on what it takes to become good at space engineering or space sciences, as well as how we teach students today. Because a mathematically rigorous approach to orbital dynamics is the standard way to teach. That makes perfect sense, of course, because they need to understand how to do it. But it doesn't impart them with a useful intuition about orbital dynamics. It doesn't impart them with an intuition to look at a map and say, this is how I would get to Jupiter in the next year. And that's something that maybe we can solve. And so, looking at these problems, I sat down about a year and a half ago and said, oh, why not we come up with something to do to maybe get me practicing my C++, because God knows I need it, and maybe learning a little more about orbital dynamics so I can move forward. And I started a very small coding project, which became something very different. And that project is now what we are using, my team and I, to try to tackle one of these problems or two of these problems in an individual level, and it's called Project Voyager. Voyager is, in essence, a space mission planning suite. It's meant to be used for educational purposes and for young startup industry. It allows mission planning over distances from interplanetary within our solar system, cislunar, and to the moons of other planets, and eventually even to other star systems within 15 light years. That's the scope of our software that we're developing. Now, as I said, it's meant to be used in education. It's meant to be used in industry. For education, we're intentionally designing it to have the simplest learning curve possible. We're using concepts out of video game design, which is becoming a much larger industry, and we can utilize that for science software development because they are very good at designing things to be easily accessible. That takes care of part of the education problem. If we can use visual software to teach students orbital dynamics, their intuition goes up a lot. Show of hands, how many people have heard of a piece of software called Kerbal Space Program? Awesome. How many people have played with it? Awesome. How great is it? Yes, okay, perfect. So, thank you. Okay, so Kerbal is a great game, but inherently it's a game. And because of that, it's very difficult to move into the realm of reality from a teaching perspective. To approach the educational institutions and say, you know, we can use this for teaching is difficult. Where we can come in is effectively to say, well, we have software that works very much the same way. You don't have to design ships to conform structure, though that will be available eventually. But you can actually teach them from the ground up how to make an orbit work, how to get from point A to point B anywhere in our solar system and eventually well beyond. Now, Voyager started, as I said, about a year and a half ago, or almost 2 years ago now. It was a very small coding project. I was in my 4th year of engineering at UFT. I'm an electrical engineer. And I wanted to relearn C++, which is a programming language. And frankly, because I was very bad. And I thought, you know, I'll build an in-body gravitational simulator. I will build a gravity sim so I can practice my orbital dynamics, I can practice some space flight stuff, and maybe some space trajectory work, and I can build a really cool program. I said, fiddling away on my computer and making absolutely nothing that worked. I went down to Starship Congress in 2013, met some absolutely wonderful people, most namely Mike Mongo and Andreas, who I talked to for the entirety of the conference, and who thereafter I stayed in pretty good touch with. I was graduating university, and about a few months later, and this project was still going, and it had started gaining some interest. So I said, you know, maybe I should do something with this. Talking to the guys from Icarus, we decided that we could actually spin it into a full-blown project under Icarus. This little simulator software design could become what I described Voyager to be. We scoped it out, we built it up, and I started building a team. After Starship Congress, I started building a very, very good team, and my team is entirely made up of students, undergraduate and graduate students from the University of Toronto and surrounding universities within the general Toronto area. And we started taking on not only engineers and coders, but astrophysicists, general physics students. We have at least one political science student, and we're starting to take on graphic artists. We have a very powerful multidisciplinary team that I'm very proud of. Yes, you do. I'm very proud of, and they're doing absolutely amazing work. And we've been working on this now for a year and a half, developing the software from the ground up. Now, my team, as I say, is made up of a very multidisciplinary group, and the benefit of working with students is twofold. First, going to the issue of celebrating each step, it provides me the opportunity to give students in undergraduate studies an opportunity that I didn't have when I was studying, which is to be part of what is becoming a very meaningful space-related project that might have legitimate repercussions, possible ones within the industry, and help the industry grow. The second benefit of recruiting students is, as ironic as it may sound, they usually know absolutely nothing about what you're talking about when you start. They have no idea what they're doing, and to be clear, neither did I. But this is the fun part. Students, more than anyone else, are dedicated to learning. That's their job, effectively, until that point in their life, until they finish high school if they leave then, or university, or perhaps graduate studies. That's all they do. They learn new things. And if you give them something that they're interested to learn about, they will become experts on that subject. And what they can create with those quickly developed expertise is unbelievable. Voyager used to be several really crappy lines of code on my computer. It used to be a couple of line drawings in paint. Really bad line drawings in paint, I apologize. It used to be some even worse line drawings in paint to describe orbital dynamics. I give this to some members of my team early on. We discuss how these things work. We do about 2 weeks of research in orbital dynamics, and we have a functional simulation of the same thing in Hackathonics, accurate with impulse curve. This is the power of what you can do when you have students working on something. And what's important for those students and those young professionals is that these things have major repercussions. Everything that they learn, everything that they build through this intake of knowledge and through the belief that what they're building is actually potentially important, is they build something that will actually be potentially important. It's something that can actually affect industry in a positive way. Now, Voyager, what we intend to do with it is to provide it to academic institutions, to provide it to young industry. We're actually moving a little bit into an interesting position with our relationship with Icarus, and that Voyager is becoming a company in Toronto very shortly, which I'm very excited to say. The project has moved much further than I could ever have imagined it going. Now, I did promise. I'd like to give a brief demonstration of the software because I talk about it a lot. A lot of my talking, I find, doesn't give a good enough indication of what exactly we're doing. So I'd like to show you Project Voyager as it exists about 2 weeks ago. The most recent version has some bugs, so forgive us. But I'll show you Voyager as it exists about now in the 3 major components that make up the software. First is the space map, as I mentioned. Our map encompasses the entire solar system. A 3D interface built on the Unity game engine. This allows us to port it to any output system. We can put it on Linux, put it on your iPad, put it on an Android phone, and, as has been suggested recently, and as we are going with, make it a web-based application so that the average usage of the computer, or so the average strength of the computer a person is using, doesn't matter because it'll all be powered server-side. This means anyone in the world can use the software with a crappy computer and access to the internet, which is phenomenal because it means that not only does this potentially give a new tool to members of industry, it has reach. Oh, this is a buggy video. Well, that's unfortunate. It'll bounce around. The point is, the map reaches out to approximately Pluto's distance and range. We have all of the major planets, as well as Pluto. We all have a deep recognition with Pluto. But it reaches all the major planets as well as all their movements. This is all data pulled directly from the NASA Horizons database, and we're using ephemeris data to produce Keplerian orbits of the planets. This is an inaccurate approximation. We know this. We're currently working on upgrading the entire system to directly pull ephemeris data constantly, every day updating. And since it's a web-based application, the server updates, everybody else updates as well. We can have accurate running of the entire solar system for the next 50 years until the new frame of reference is devised, probably 2050, at which point we can upgrade the system because it's already up to the database. The map is very inclusive. We have all of the gravitational effects of every body, major and minor, being accounted for in the system. I'm sorry, this is so buggy. Okay, if you're all really nice after the conference, I'll actually demo the software for you in person. But, whoa, hello, okay. Now I'm embarrassed. Long story short, the Voyager software keeps track of all of these things in a detailed map, and this map itself is dynamic. It wouldn't be very useful if it was just a basic map. Our start date right now, which is arbitrary, is something like August 1st, 2014, but we can move time forward and backwards through it and get it done. If you guys can excuse me for a second, I'm going to try to fix this, because it's actually a very nice video. It's actually a very nice video, and I would very much like to share it with you. There we go. Better? Okay. Okay, awesome. So the map itself is dynamic. We can effectively produce or reproduce the motion of any given planet over any time frame within the James 3000 frame of reference in the Horizons database. And their positions right now are fairly accurate. With the pulling of the ephemeris data proper, which we should have within the month, they will be as accurate as we can have based on the data available to us. And as our knowledge of the solar system, and it's happening again, well, as our knowledge of the solar system increases, then we get more information on more asteroids, more comets, new systems.
Try playing it with, without being full screen.
Okay, fair enough. Sorry, guys. This is stunting the top a little bit. And now the computer's frozen. Okay, well, you know what? We'll skip the video on that one just to keep it safe. Now, in the map, it wouldn't be useful with just a map. We have an application of Hackathon. Now, for those of you who aren't aware, Hackathon is one of the simpler ways in which you can plan spaceship missions, do vector mathematics to determine where a ship will go over time in space. It's based on the fairly simple principle that at any point in the universe, there's only two objects. There's the ship you're on, or the ship you are, and the planet that's proportionally, based on its mass, closest to you. This approximation works very, very well for doing things very quickly and can be solved algebraically, which means that we can not only solve it forward and say, you know, I do a burn of this much thrust at a certain point in the map, and then I see the orbit move immediately to the thing. I wish I could show you now. But you will see the orbit move immediately because it's part of the visual interface. The speed of these calculations is effectively instantaneous because in Hackathon they're all algebraic, which is amazing. We have several methods we're using to solve depending on the types of orbits, but all of them have been rigorously tested and are continuing to be rigorously tested so that we can meet flight quality. We're in communication with a couple of organizations that do independent software verification, specifically so that we can handle the level of accuracy that's expected in the industry. Now, this is great, that the patch comics is wonderful because we can effectively use this to plan missions and get a good idea of how much delta V we need to acquire, and then based on your ship, how much fuel you need for any mission within the solar system. But patch comics, as I said, suffer from some inherent inaccuracies. Things like Lagrange points cannot be appropriately modeled in this system because they require at least 3 bodies. So the simulator that I built, the crappy little simulator in C++ makes an appearance again. The simulator has been completely redesigned by someone who is not, and has been built into the system so that we can take the basic mission plans that people come up with, and then much more accurately run them with a high-caliber simulator through a full n-body gravitational simulation, using the mass of every object in the solar system that we're accounting for, and that, again, to be clear, can be completely extended. We can create much more accurate approximations over time. So if we have a basic mission here, which for some reason now is working, in a fairly high orbit around the Earth, and we want to simulate that, we'll simply set up the parameters, say when we want to start the simulation, when we want it to end. We'll choose the step size. We're using, just in case anybody's interested, a nice 10th order approximation that does not have a variable step size. So we choose the length of time we want to simulate for in real life time, choose the step size, and we're going to choose 1 minute here, and I'm going to fast forward the video because it actually takes about 2 minutes to simulate. And it'll overlay on the map, it'll overlay on the map a more detailed simulation. The blue line, the light blue line that you see here that's making a sinusoid around Earth's orbit is exactly what you would expect in an accurate simulation of a circular orbit around Earth. So we can do these simulations. We can do the simulations for maneuvers. We account for them based on time of flight. The long and short of it really is that we are starting to build, and we've basically built all of the base functionality you need into the software. Now, there's a long way to go with it. To be clear, there's a very long way to go with the software. We are not only in terms of development, but in terms of business work, in terms of figuring out what the industry needs exactly. How do we include that functionality there? But the long and short of it is, the core physics is there. We built the physics engine, and now it's all about extending it to create the utilities that are necessary for the industry and for education. What's wonderful about this project is that Voyager is a perfect example of an enabling technology. It's a perfect example of enabling technology for navigation, potentially, for mission planning, and for education, which brings us back to the basic talk point, which is, again, how do we get there? Now, Voyager is a great tool for education because it enables inherent visualization and a visual nature that students don't usually get access to until much later when they get create visuals for themselves in MATLAB. It lets people play with this stuff and a very real-world version of this stuff, as opposed to Kerbal, which is fun, but again, very complex and not exactly realistic physics. If we can use this as a tool in high schools and universities and colleges to better teach a new generation of students how orbits work, how orbital mechanics work, how spaceflight works, then we have an entire generation of people who are going to be more aware of the problems and the tools that they need to be developing in the space industry. Voyager, just like the tools I was explaining more generally, gets the development of more systems. In the young space industry, composed primarily of young startups, CubeSat companies and such, Tools like Voyager that are inherently accessible, designed from the ground up to be accessible, to be visual, which means they can report on it and give reports to different people, as well as external reports that allow people to see what they're doing and understand what they're doing. These things will allow them to have a better chance in the market of survival. So many space companies today are created and then fall apart on the basis of it's very hard to prove out a concept. With tools like this, it becomes much, much easier. With consulting services of people who are experts at this, which my team now has the competency for, people can build better and more reliable systems that get us further and further along in our journey to explore space. So this really does bring us back to the basic question, which is, how do we get there? And I think I've shown you how we can really come to an answer here, and what the answer is. If we can change the focus, and instead of celebrating only the massive achievements, the final steps, if we can start teaching that you need to celebrate each individual small step, each incremental step along the way, we can show students, young professionals, and experienced professionals alike that you can make major, major differences in space industry. You can bring us much closer to where we want to go. You can bring us much closer to exploring the universe, being on these massive spaceships that we dream of, by working on small things, and those things have merit. Hands up, who's heard of the Rosetta mission? Land on a comet. It's amazing, yes? Yeah, it's amazing. On that day, I remember I was sitting and watching the Rosetta mission on TV because it was being streamed live, and more people than I had ever known was being interested in space were watching that mission, because it was phenomenal. I mean, we haven't had many major space breakthroughs in my adult lifetime, so I don't remember many of the ones of my youth. And that was phenomenal. So many people were excited about that, and so many people were celebrating this amazing thing that the ESA had accomplished. What I'm trying to suggest is that it's just as important that we celebrate, maybe if not to the public and the layman, within the space industry community, we celebrate the engineers who developed the harpoon gun about a year earlier. Because without that harpoon gun, it wouldn't have been possible, despite the fact that it bounced and ended up not using it. It wouldn't have been possible to make that mission work without those enabling technologies. And not celebrating, and not publicly saying, wow, you guys did something that gets us closer to making this work, is inherently detrimental to all of us, because it allows all of us to not look at the little pictures that are necessary to make up the whole of where we want to go. So the answer to the question of this talk, how do we get there, is quite simply to put one step in front of the other, one foot in the front of the other, and move forward steadily with each other, building these enabling technologies. And before you know it, we'll be at the stars. Thank you very much. Questions? Yes, sir.
Is it an open project? Is it on GitHub? If people want to try and contribute to the code base?
No, absolutely. Right now, it is not an open project for a couple of reasons. One, that as I say, we're moving into a business structure, and we're trying to better understand how to make that transition. And until that transition is made, we don't want to potentially risk open sourcing the code accidentally until then. However, to be clear, right now, I'm very interested in expanding the team in terms of coders and people who are interested. If people are interested in volunteering for the team, to be clear, we are all volunteers at this time. I've been doing this for 2 years. I'm the only person on my team who's not a student, and it's only because I graduated while I was running the project. And I didn't have a choice. I had to do it back. The only reason I'm not a student is because I graduated. And everybody on the team is volunteer. If anybody's interested in participating in the project or helping out with the project, let me know. I'm probably the most approachable person you can ever meet. So right now, not open source. We'll find out.
Okay, thank you.
No worries. Yes, sir.
One thing I found very interesting about this is that just raising the topic of interstellar flight is something that most people are going to respond to that. Well, that's way too hard. There's nothing that I can do to contribute to that. So I really give you my kudos for demonstrating that. Yes, there are things that you don't need to be some 40+ years star engineer in order to accomplish anything worthwhile.
Thank you. The way I usually look at it is, not everyone is Nikola Tesla. Not everyone, because they're born to invent wireless power transmission. For the rest of us, all progress takes work. And celebrating each step of that work is just as important as celebrating when a Nikola Tesla comes up with wireless power. Not doing that doesn't deserve flawless. Yes, sir.
Do you have any positions for anyone who can't code?
I apologize, I can't hear you.
Do you have any positions for anyone who can't code?
Yes. We are divided. So my team is made up of I didn't mention this. My team is made up of approximately 22 students, undergraduate and graduate students, as well as several experts throughout the industry who help us out with a lot of stuff. Many of them are with Icarus, many of them are outside of that boundary. In terms of the way the team is divided, we have a coding segment of the team, a research segment of the team, which is run by Nikola, who's in the second row right here. Research is made up either of engineering students, people who are not in engineering or in physics, but are very interested in doing background research, possibly writing to do with writing with software, writing to do with the project. And right now, I'm also running a recruitment phase for graphic artists because, as Sarah Jane Pell said 2 years ago, every space project needs an artist. Yes, sir.
How difficult is it going to be to extend your project Voyager to trans-Neptunian objects? You just need 2 elements or?
Okay. There are. So the question, just for everybody, was how difficult would it be to extend the software to reach physically larger distances? That question has 2 answers, and there are 2 primary difficulties in that, both of which we are currently addressing. One is how we deal with scaling the universe in the camera scope. This is a programmatic thing. And effectively, right now, we move a camera away from an object to get further away. What we're going to be moving to is shrinking the universe to get the camera further away, because as it happens, that's better in programming for dealing with large areas, because we can simply stop rendering things beyond distance. So in terms of extending the software by adding more objects, that is trivial, and we could do it tonight. We could add any object we have declaring components for, or ephemeris data for, in actually a few minutes, which is phenomenal because the software can actually be extended that way. In terms of actually scaling up the universe, right now we've effectively reached the limit with the universe size at Pluto's orbit. The way we're going to handle that is, instead, as I say, of moving the camera out, we're going to shrink the universe, and then regrow it when we get close to other things.
How about extending the software to include like a swarm of objects, like an asteroid belt?
Okay, I don't have my computer hooked up. If I did, I would show you live. I didn't. This is actually in the math video, but unfortunately that stopped playing. At the suggestion of a few of our experts in the industry, we have already put into the map something like 60 asteroids and several Kuiper belt objects as well. And many of the asteroids in the belt, many of the larger ones, to demonstrate that we have the ability to handle that load. We actually have the data for some 300,000 asteroids that we pulled directly from the ephemeris database. We can do that now. That is something that we've already been extended for. The question really is render capabilities of the server we're using in terms of keeping the software moving fast enough, frame rate fast enough to deal with. What we're dealing with, and again, I wish the video would work, but what we're dealing with right now to make these things more accessible is what we call contextual rendering. So every time you're not looking at something, the computer pretends it doesn't exist because it's a waste of power to generate. The only case in which that's not true is in the simulator, where we have to actually track the objects of everything at once. So the simulator is built to handle actually any number of objects up to something like whatever a double holds, that many objects. And that's only because you need that many indices for a single matrix. We can have multiple matrices. So right now, we can even gravitationally account for as many asteroids. And we have several in there for demonstration.
So if you had 100,000 asteroids that you were trying to calculate the gravitational effects on a particular vessel, it would do that.
It would. It would take longer. There's no doubt about that. Any simulator, the more numbers it has across, the longer it takes. It would take longer, and you might want to set size simply to make it faster, but it would do that. Okay, if there are any more, thank you guys very, very much for having me.
Our next talk is from Lucas Schrenk again, who is revisiting the podium. Lucas. And he'll be talking about the light sail.
Exactly.
The light sail competition that they won. After you.
Yes, I tried. In which folder are the presentations? Andreas, in which folder are the presentations? Hackers, that's not it.
Bottom left. Starship Congress on the desktop.
Oh, thanks. Okay, where's this? Okay, second try. This time I hope I'll be more confident. Thanks for all the kind words and comments on my last presentation. Feels good that at least I did it quite right. So my next talk is about laser sail propulsion. It was a good a design competition by, yeah, let's get to it later. So I'll just, not interesting. Yeah, by I4S, the Initiative for Interstellar Study, founded in 2012 and now a non-profit organization in the UK. And they started the design competition about an interstellar laser sail propelled starship to get international students on the project, work together to compete with each other. The idea is basically to keep the complex part of the system, the propulsion system, close to Earth, where you can maintain it, where you can update it, upgrade it, and have the ship, a less complex system, flying to the star system that you want to go to. And our boundary conditions have been that we reach the target system within a century. Our laser power, beam power should be below 100 gigawatts, and we should use near future technology. So how did we address that problem? We started with the laser. Where should we position it? We could put it on Earth. There's easy access, but we have atmospheric disturbances. We could put it on a satellite that makes it highly flexible. Where you point it, we can use it for different future missions. But you require station keeping, which increases your costs. You need propeller. And said, okay, let's combine the advantage of placing a laser of those two and placing the laser system on the moon. To reach Alpha Centauri, you have to be in southern hemisphere, so we put it on the lunar south pole. There you have no atmosphere, obviously. You don't need station keeping, and the moon is reachable with near-term technologies and in the near future. That's just the advantages. This is much apart from the fact that it is difficult to put the 100 gigawatt laser plus the power system with 400 gigawatts somewhere. It is even difficult to put it on Earth. So, considering this difficulty right now. So a system with power. One requirement was to use a space solar power. That doesn't sound good. Let's try this. Yeah, we said, okay, let's assume 40% efficiency, 250 gigawatts. That's a really large collector, 21 times 21 kilometer of solar collector. It is heavy and it is expensive. So our conclusion was it is not a good idea to do that with space solar power, at least with the technologies we have right now. The alternatives, I don't know, maybe we will have fusion power at some point. It might be a good alternative to a power supply. Then we looked at the laser. They're basically just military lasers that fulfill our requirements, free electron lasers and diode lasers, because they don't need fuel that is used up. So that were the considerations. Just have a really robust laser system. That's why we just based it on current military technology. Next thing was we need an optical system, because like I guess laser beam diverges over distances, and if you're talking about interstellar distances, it gets more and more important to really focus your beam. One proposal you can find in literature is Forward's Fresnel lens, 1,000 kilometer diameter. Our first intention was, okay, where do you put that? You have gravity gradients with that size that will just tear apart your lens. So we are going with smaller distributed laser arrays on the lunar south pole that can afterwards be reused for other missions, can point it in different directions, and it's easier to point them because the whole system is smaller, and this diagram just shows what achieving the pointing accuracies should be when we want to accelerate at a certain distance in light years. And that's in the order of 10 to minus 12, 10 to minus 13 rads, which right now is not achievable, not from Earth, maybe on Moon, because there's no atmosphere, you can really try to point your system. But we're not experts in that, so we figured it's difficult. The next thing then was what kind of laser cell material do we use after we had the propulsion system located on Moon. We need high reflectivity, low area density, and a high operating temperature, which sizes your determines your minimum sail diameter to account for the 100 gigawatts distributed on the surface. We looked at the luminous mylar. That's too heavy, but it has a high reflectivity. We looked at pure graphene layers. They have a low density, really nice material, but a high transmittance. So basically everything goes through. That's why in the next step we looked at, can we have more layers of graphene? And from our basic analysis it works, so you have secondary reflections inside the layers and thereby increase the absorptivity and reflectivity. Like you see here with the number of layers, the force that you can put on that sail increases. But we also put alkali atoms inside to adapt the optical properties, but that made it heavier and the operating temperature decreased. But we found out that the minimal radius that could be achieved with just graphene is not optimal because it's very small, and to point at that and is not very optimal. And we also have a magnetic sail that I already talked about. And we said, okay, we want to reuse structures, take as few mass as possible with us. So we put a constraint on that. All the technology and pre-analysis, we started to do emission analysis. The standard phases, acceleration, and the cruising phase in between. To reach our requirement, we need approximately 4.35% speed of light. And then we started, and after acceleration was easy, then we had to use deceleration. We have a magnetic sail, I talked about that. The important part is that it is more effective at higher speeds. That means once you drop to lower speeds, your deceleration force just decreases to an amount where you cannot use it for 100-year deceleration, for a 100-year mission, sorry. So we looked at a different system, the electric sail, that's basically charged tethers that interact with incoming ions in the interstellar plasma. And it has an optimum at lower velocities. So we said, okay, in the next step, let's combine that. And we started with a magnetic sail, and when the acceleration of the magnetic sail would have been the same like with the E-sail, then we switched from magnetic sail to E-sail. Like you can see here with the blue line, the duration to decelerate is lower than just with an electric sail or with a magnetic sail. That's just a repetition of what I said. We said, okay, let's use the same structures. So the deployment beams for the laser sail also are there for the magnetic sail. And here you can see the results that we have done for spacecraft masses and mission duration. And we found out that we could use a design point with 4 tons of spacecraft mass. That's excluding all the sail masses, but 4-ton spacecraft mass is not payload. So that's the whole spacecraft, and we assume 12% payload fraction for that, which leads to 500 kilograms of really usable payload for scientific research. Just a few parameters. Our laser sail diameter is approximately 19 kilometers. Just to give you an overview of how large the ship is. And just short mission description that we came up with. Then we accelerate with the laser sail, seen in this picture. Then it gets disposed. We decelerating after cruising. We decelerate with the magnetic sail. Then we get rid of the magnetic sail and still have the e-sail for the last bit of the deceleration. And with that, we can make it in 100 years. And interesting fact, we go to 9% the speed of light with that ship to reach the 100-year. That's pretty awesome. And you hope that you don't hit anything at that speed. Okay, just quick for the subsystem, because we had to do a subsystem analysis. Power system was very difficult because we had a long lifetime, but low mass. With Icarus, we gave it up to have low mass because the rest of the ship was just too heavy. We didn't even consider lightweight power system because that wouldn't have done anything to the overall time. But here, when you have only 4 tons of spacecraft mass, every kilo counts. So in RTG, when you take that with you, you need high initial mass to do the decay. Solar panels, you need sunlight, laser light, but we have an electric sail that could be used as an electromagnetic tether, and by not charging it, the incoming ions in the interstellar medium would produce power for us. So we combined that. We have the electric tethers when we don't use it as an electric sail, and we use the solar cell when we don't have the electric tether. So we need power for deceleration, and for that we said, okay, we have 100 gigawatt laser, we just widen the beam and try to hit the spacecraft and transmit some power to that. Communication system, same as before, interstellar distances, large losses, so we need large antennas, but fortunately we had the structure of the laser sail. So one idea was just reuse the laser sail. For now we haven't gotten to that because we said we want to get rid of it. It has some mass and it helps us for deceleration. So we looked at the 2 standard options, laser and radio frequency. Some communication architectures like just directly sending it versus sending it from Earth, reflecting it at the spacecraft and sending it back, which would require less power at the spacecraft. But there you have just really high losses, so that was discarded then as not feasible. Or you put the large sail in between Earth and Alpha Centauri and try to modulate the light coming from the star. Sounded like a good idea in the beginning, but the signal-to-noise ratio that we calculated was just not good enough to get a signal back. And we stayed with the standard architecture, put a small laser system on top of the spacecraft and used that for communication. Just shortly about the payload, there are different science goals that you can achieve, just stellar observation, lander, and the ultimate goal, the search for life. So we would like to have telescopes, orbiters, and landers. Our conclusion was it's difficult to miniaturize some of these systems. That was one of the ideas in the competition to combine laser sail propulsion with CubeSats. But so far we don't have a CubeSat-sized planetary lander that fits in 500 kilograms payload. So we said for first mission, we just send a telescope that observes the system and have some small nanosatellites, like a swarm that you can send to interesting areas in the target system, like shown here. So we don't know yet if there are planets. We've seen some. We don't know where exactly. That will change over time, so the mission has to be adapted. And once identified and interesting regions identified, we would send the subprobes there, the CubeSat probes. Okay, that just shows our system again. So we have the communication system, laser, that's the telescope, I guess, with some thrusters. Basically, yeah, that's to our conclusion. for such a long duration mission, high scientific yield is required, and that's not feasible with the assumptions we had been given and that we had made. So we would need a larger spacecraft, but like you see here, with the mass increases, the power increases, and that's in the region we looked at. It's close to linear. So we would need really high power laser. But our conclusion was that we would have to increase the mass by 1 order of magnitude, but increasing from 100 gigawatts to 1,000 gigawatts beam power, with then 2,500 gigawatts of real power that you have to provide. That was, in our opinion, not feasible. So the final conclusion was that we have miniaturization problems and also pointing requirements that we cannot fulfill. So the whole concept should be revised. That was our recommendation to I4S. Thank you for your attention.
Any questions for Lucas?
Yeah.
You talked about using multiple small lasers, but wouldn't the diffraction limit on focusing be a big difference to that idea?
So the basic idea was having that laser, letting it refract to the whole size, and it has some flaws. I totally agree on that, but it was, in our opinion, more feasible than one large optical system that you have to point and adapt. And we said with smaller ones you can go with adaptable focal points and stuff like this. So I'm not an optical expert again. You may ask what I'm an expert on, but I'm not sure. So my expertise is spacecraft engineering. Yeah, I don't know if that answers your question, or there are definitely some problems with pointing multiple lasers on the spacecraft, on how the spacecraft will react if you mispoint some of them and not equally distribute the power on the sail. So we might have to reconsider that. Further questions? Okay. Thank you.
I wonder if we can solve this problem. Actually, let's see if we can find it through recent documents. Frog. Oh, yes. Okay. Is this if you're right? This is a pointer. It's a pointer and our next and final speaker for the day is Bruce Mackenzie, who is the founder of the Mars Foundation and is dedicated to education and research on the settlement of Mars. His special interest is in the use of in situ materials, such as the production of plastic and masonry from the Martian air and dirt, to build habitats and 3D printing for Mars settlements. Bruce has been active in the National Space Society, AIAA, Mars Society, Space Studies Institute, and SEDS. Other work includes entrepreneurial ventures, software engineering, aerospace engineering, CAD development, GPS receivers, gun-launched satellites. But the most fun, as he states, were Mars settlement designs, space elevators, and the use of rotating space tethers to establish industry on Luna and export lunar materials. Please welcome Bruce Mackenzie.
Thank you. Can you hear me in the back?
Yes.
Good. You're in. Okay. So let me put in a little plug. The Mars Foundation can use help with trying to figure out how to live and build on Mars, extracting materials, construction, architecture, publicity. And also for you students in the audience, I'd encourage you to look up SEDS, the Students for the Exploration and Development of Space, and form a chapter or affiliate, or just get in touch with them. Okay, let's see. I'm also for the following thing called leapfrog, I could use people helping, collaborate, especially working out the energy, the mass, and the velocities involved. This is really just a conceptual thing. Okay, to get started, Interstellar isn't really thinking big enough. What do you do after you get to, a few stars? And I propose something where multiple spacecrafts carry us across the galaxy to multiple stars. Let's see if this works. Yes. Okay, so I'm assuming this is sometime in the future. Everybody, I hope, knows about orbital settlements, Jerry O'Neill's space colonization ideas. Okay, if you don't, look up ssi.org.
Excuse me, Bruce. Sorry about that. Yeah. Sorry.
Yeah, I didn't want to. No, it's too loud now. Okay, but you can. Good. Okay, sorry. So look at ssi.org if you don't know about orbital settlements. But I'm assuming that at some time in the future, we will be able to go out to asteroids and convert them into building materials and make orbital settlements. They can be spinning for artificial gravity. There's one up in the upper right under construction, and what it might look like inside with houses. So I'm assuming we can already do that, and assuming that we can already launch at least some things to an interstellar trajectory, and that we have energy storage to keep these things going. Okay, now why not just have a orbital settlement going to another star, as shown in the lower right? Down in the very lower right corner, you see that red and white glow? Picture that as a laser pushing you out of the solar system. In reality, you probably have lots of small spacecraft and use the same laser over and over again and then rendezvous en route. This proposal, you don't need to slow down at another star system. That's a major difference. Okay, so you have assume it's a human generation ship for now. I'll talk about that later, but assume there are people on board and you're living there generation after generation, a generation ship. Down in the lower right, there's this dark circle. That is why my crude graphics of the interstellar ship. It drops off other small spacecraft. The interstellar ship has a laser, it pushes them backwards, decelerates them. And those small ships then, so as you pass a star system that has asteroids or planets, you push these little seed ships backwards and they fall into that star system. And there are people or some kind of automated equipment, and as an exercise for the reader, your job is to start a civilization in that star system. Okay, that's possibly harder than simple interstellar flight. Okay, so there's a picture. You're on board that star sail, you're being dropped off at a star system. Your job is to, start an industry. Any clarification needed? I'll take questions at the end, but anybody have a question for clarification? Okay, now what I didn't show you was covered up by that lower left picture. So this starship has done this multiple times, dropped off and established civilizations several places along, and now more starships follow. So does the laser work? Okay, so here's the first starship dropping off to settle that planet, but it previously, maybe, hundreds of years ago, dropped off and started a settlement here. Now there are people there who have built a big laser and they're launching supply ships. And here's the first interstellar ship, the second one, the third one, and the fourth one. They're forming a convoy. So these third and fourth ships are receiving supplies from the settlement that was created. So supplies of some kind of stored energy and matter. By the way, it's nice to have an audience that I can comfortably talk about interstellar flight. This is kind of beyond it. So, yeah. Okay, and also you can do, you can pass close to a star and do do a gravity turn to aim at another star system. Lots of problems, obviously, but it's pretty much the same technology as for interstellar flight. So if we can get to another star, then we can go to multiple stars. So this is what I call the convoy or the leapfrog. Any clarification needs on this slide? Okay, let's see what's next. All right, so initially assume there's a bunch of people living on board. They're living for generations, something like an O'Neill 7, so a giant torus in the upper left. There would be people on board, both the supply ships and these siege ships. So, whoops, wrong button. Okay, so here you are in your interstellar ship. You pass a settlement, and they launch dozens and dozens of these little craft out to join you. Velocities would be a tiny fraction of the speed of light. We're talking thousands of years. But once you get started, it just keeps going. Okay, so human ships. At some point, we may have artificial intelligence. We may decode human intelligence and download our intelligence into a machine. Obviously, then the ships can be made much, much smaller. Something the size of a bacteria could have the more computational power than our desktop computers. So we could be talking fairly small automated ships at some point. I still consider those to be our descendants because it would be our intelligence in them. I don't really want to get into a philosophical or religious discussion, but I'm hoping that someday we won't be compelled to carry human bodies to the far side of the galaxy. Also, if we do have artificially intelligent ships, or they'd be willing to take more risks. And it's also fairly likely that if there is a colony, a generation ship with people on board, they would be very interested in doing, the research toward this kind of automation. So you might actually improve the ship as you go along. The people who'd be most interested in this scheme would be the people who were on these ships or in the settlements that they left behind. Because this slide is too much information, I'll skip it. Many different kinds of propulsion could be used, light sails, laser, microwave. This is a laser that is then collected and drives an ion thruster. Could be fusion power, possibly fission power. What I'm talking about is a concept that is somewhat independent of the propulsion mechanism. Concept of just getting out there, keep going, don't stop, spread settlements as you go. Robert Forward gave proposals where he's talking about over there in the far right, 1/10 of the speed of light. He's also, unfortunately, talking about 75 million gigawatts. I have no idea what a million gigawatts is, much less 75 million of them. But someday the technology is just going to keep going, and we really don't know. At what point these will be practical. At what point we can use automated systems to harness a lot of energy and matter. Okay, the lead ship eventually runs out of material. So you're dropping off all these craft, all the craft you drop off need energy and mass, and the lead ship just gets lighter and lighter, uses up all its stores. So here's where the leapfrog comes in. Starting in the lower left, you've got 4 ships in a row. The first ship is this red square. The 3 ships behind it are picking up, replacement supplies of matter and energy. They keep going in a straight line, dropping off and establishing settlements as they go. Again, this is hundreds of thousands of years. The lead ship is getting light, takes a detour that's longer and falls in behind them. And now the original 3 ships are establishing settlements, and they can provide supplies. Those settlements provide supplies to what had been the lead ships. So you take turns being the lead ship, or the other ships leapfrog over the first ship. If you get enough supplies, you could build the interstellar ships larger, you could divide them, you could go off on different routes, you can go in a circle. Any clarification on this leapfrog concept needed? Either everybody understands it or not. Yes.
The very first ship.
Yes.
Is that the one down in the bottom right corner?
Yes. So the first ship is the red square. It's depleted a lot of its supplies. Doesn't have anything more to drop off. It takes a long route, doing gravity turns around a bunch of stars. Goes down to the lower right corner, comes back up. That's a longer route, takes longer in time. The other 3 ships pass it, they leapfrog it.
And then it gets back in line with the rest of
It gets back in line at the back of the line.
Okay.
And then as it passes newly established settlements, they provide supplies to it and rebuild it. Okay. Again, we're talking really long time frames. Up in the back?
Yeah, this trajectory for the first ship that makes it basically to take a longer route.
Yes.
Is that established at the very beginning?
Okay.
Solar system escape velocity, or is it propulsively
No,
obtained?
not propulsively. You have to take a close pass past some stars to turn your trajectory. And
you don't plan thousands of years in advance.
Well, you really can't plan it in advance, because as you get closer, hopefully your sensors will be better and better, and you're going to want to say, is it safe to go near this star? Is it full of debris? Were there planets that swept out the debris? How close can I safely go to that star? Would it be a good place to establish life? And one of the problems is, how do you make these decisions? If you're 10 light years or 100 light years in front of the ship behind you, you got to make decisions faster than you can communicate. So, there was another question somewhere?
You kind of answered it, I think, but I was wondering what distances you were picturing between the ships here.
Yeah, what distance between the ships? I would like to find a couple of people who want to sit down and come up with a couple of scenarios. But the distance between ships, really the time between ships, has to be enough to drop down small pieces of equipment, that are somehow intelligent, and start manufacturing, bootstrapping more and more manufacturing, constructing lasers or some other power source, collecting energy, and then helping the ships that follow. Maybe 100 years. Could be 500, could be, with automated equipment, could be 50 years. In the back.
2 short things. First, the red depleted ship still have enough stuff to go on maintaining itself, but not to sell to new colonies, correct?
Yes, the lead ship, assuming there are people on board, the lead ship would still have enough to maintain their life support. All these ships have to repair themselves, because you're out there for thousands and thousands of years. So it's not an easy job. But now, if it's an automated ship, you might just dive it into a star and say, it did its job, its job.
The ships on that upper sort of bridges, B, C, and D, they become new colonies.
Right, yes. Yep. And I showed 4 ships, the minimum is 2, there'd be benefit for more. Let me keep going. Sorry. Okay, technical challenge, yes, there's a lot of them. There's every technical challenge you have for interstellar flight, except for slowing down. Propulsion, energy, life support, the energy for life support, repairing your spacecraft, building, you may want to enlarge the colony ships, the convoy ships, and split them, sensing what's ahead of you. You might want to do a lot of research and development en route. So, Okay, societal issues, possibly harder. How do you establish all these societies that will be stable? What's the minimum number of people? Assuming there are people on board, how are they governed? What happens with disputes? I threw in religion. You might want to even instill in the people you send off a set of morals, almost a quasi-religion that says your mission in the universe is to help the people behind you. Your mission is to boldly go and establish new civilizations who will then help other people go and establish new civilizations. I'd hate to have hard feelings between two of the ships, holding a grudge. And I mentioned how do you plan ahead when you have many years of radio delay communication. Okay, if that wasn't big enough for you, okay, let's say you're here in the Milky Way and you establish a long string of settlements in a straight line that just happens to be pointing at another galaxy. You usually get thousands of settlements all lined up in a straight line. They all have lasers. And now you send some little tiny seed ships, and they go down this line and they get a boost from thousands and thousands and thousands of lasers. And they're headed off to Andromeda. So, this can be extended to intergalactic travel. Step 3 is you coast using minimal power, but step 3B is while you're in group to the other galaxy, figure out how to stop, because you don't have a bunch of lasers that are waiting for you. So anyway, so just for you people who don't want to read, one proposal is go around so you have a whole bunch of ships going out to another galaxy. You do these gravity assist maneuvers to go around in a circle, and then you drop off the seed ships, and lots of, all the convoy ships decelerate the seed ships as they pass. That's not a very good scheme, but you won't have a lot of help when you get there. So let's see what's next. Okay, I'm coming into the summary slide. So basically I'm saying this civilization would basically not be limited to the resources of the Earth, not limited to the resources of our solar system, or not even 3 or 4 stars. By the way, I will gladly send out this PowerPoint to people who are taking pictures. So most interstellar proposals, you only go to 1 star system. You have a lot of trouble stopping when you get there. You may try to live there, but there's not necessarily incentive to keep doing that, or for the people at Alpha Centauri to go on to the next star system. So this is basically establishing a culture of continuous expansion, not unlike some nomadic tribes. And as I said, I would welcome help from people. So here's the slide I'll leave up. So the summary is you get approximately 4 ships following a line. You establish civilizations as you go. The lead ship gets leapfrogged by the other, falls back in line. Was that thinking big enough for this audience? How much time? Questions? Yes.
Yeah. Once a ship commits to a detour vector, proper motion, the star may not even be there.
Right, yeah, proper motion of the stars, yes. So the stars do move within the galaxy. We're also rotating around the galactic center. You have to take that into account. And if you establish... Yes, I know, but
you can't measure it over decades.
well, this is going to take centuries. So yes, but it's sort of like navigating a ship at sea. You see something floating there, and you try to pick it up. Well, it's going to move. So yes, you have to navigate among the stars, taking into account their proper motion. For that intergalactic thing, where I said you want to have a straight line of thousands of settlements, those are going to move too. and you need to take that into account, or have multiple stars. And if there's 4 ships, the third one might take a detour and establish a civilization somewhere else, or maybe you establish a civilization on a star that is moving, and be interesting. Let me take another question. Yes.
How big did that your seed ship end up being?
How big did the seed ship end up being?
I'm sorry, I forget what it was. I was curious about the expenditure.
Yeah.
The first one built.
Yeah, we have to be careful about the terminology. So these are convoy ships. They're pretty big. They go out for thousands of years.
Square.
Yeah. And the seed ships, I don't show on this slide, they're the ones you drop off, and the supply ships are the ones you pick up. It depends on the technology. If there are people on board, the seed ships you drop off should have, maybe a dozen seed ships with 2 people each, or maybe, just a few seed ships with 100 people each, plus additional seed ships of cargo and equipment. So you're talking, hundreds of tons. And then the convoy ships, the big ones that kind of stay at sea, they never go into the harbor. Those have to be built from asteroids. You want to send them out with a lot of useful mass that they can construct with as they go and repair. One of the biggest problems is energy. You really want something like stored fusion fuel or antimatter on board so that you can keep these things alive for, in between stars. That's the real advantage for the automated ships is energy. I didn't really answer your question. We cannot estimate the size of these things until we come up with details. The real question is, what's the minimum you need to drop off on an asteroid to mine it and turn it into the minimum size factory to drop on an asteroid that can make another factory? That's the real question. Up in the corner?
Yeah, I like how you went to that point, because that's the one thing we could start working on now-ish, like in a real sense, and build facilities that could automatically build structures on other planets.
Yeah, so
and that could go all kinds of directions, including.
Right. So to repeat what he said, that's something this group could work on, is what's the minimum sized ship to arrive at another star system and live there. By the way, that's what I'm doing, running the Mars Foundation, is what's the minimum amount of equipment needed to send to Mars to bootstrap industry. Questions from anyone who hasn't asked anything before? Yes?
Are you considering a similar concept for colonizing Mars, basically having a ship that just goes between Earth and some orbit between Earth and Mars that has some developed
Okay.
and then have ships to stop with that as the.
All right. Am I considering a similar concept for settling Mars? No, I'm not. We could send equipment straight to Mars, aerobrake in the atmosphere, stop. There's no reason for a carrier ship to stay in orbit. Now, if you're talking about small asteroids, it might be worthwhile to have an industrial ship that goes out and drops off something at an asteroid and goes on and visits a lot of asteroids, but not for Mars. Yes?
Concept you just mentioned is called an alternate cycler, and the primary benefit of it would be to not have to continually accelerate and decelerate life support systems.
Right.
So it makes room for people, not equipment.
Yeah. So so you can ask me about that this evening. The Aldrin cycler or the generic Mars cyclers are spacecraft that cross the Earth's orbit and Mars's orbit. They have life support systems on board. Some liken them to a hotel. You take a small craft from Earth, you land at the hotel, you live there 3 months, and you get off when you pass Mars. And the advantage of that is that your life support system stays in a solar orbit. You don't have to decelerate and reaccelerate your life support system. And by that I mean a fairly comfortable, greenhouses and sort of a hotel.
very curious to know what kind of propulsion system would be on board, because you would need one. Every ship would need one.
Yes.
Allow you to do the overwork maneuvers you need to appropriately leave every start.
Yeah.
What kind of system are you thinking for propulsion?
So what kind of system would you need for propulsion? And you mentioned the small maneuvers for fine-tuning your course and carefully aiming to turn in the star. Again, this is up in the air. If you can plan far enough ahead of time, let's say you can sense the star system way ahead of time, you know there's no asteroids in your way, there's not a lot of debris, you could use a very low thrust, high specific impulse, ion, electromagnetic, Hall thrusters, whatever, to do a little bit of that fine tuning. In an emergency, you might jettison some mass. So if you're coming in real fast and there's an asteroid right in front of you and you're spinning, you could have some cargo that you could jettison and that would move the rest of you. Maybe what you jettison is useful to the people there. Maybe it's an exploratory spacecraft that would then go off in another direction, somewhat unplanned, and make new discoveries. I have done some work with rotating tethers, where the whole station is spinning, you extend the tether out maybe 8 kilometers, 40 kilometers. You can get more than 1 kilometer per second delta V when you release something from the tip of the tether, but that's not really too helpful for these kinds of velocities. Now, when you're picking up the supply craft, so you're passing a settlement. They've previously sent out dozens and dozens of little supply craft ahead of you, and you're slowly catching up with them. You somehow need to catch them too. Maybe they maneuver to you. Maybe you have this rotating tether, and they come in and hit the tether and get pulled in. To be determined. The point is, this leapfrog concept can be used with many different technologies, propulsion and energy. Way in the back corner.
Just a quick comment, actually. You could potentially solve the maneuvering and catching problems simultaneously by including like a laser array on the ship. Because if lasers, when they reflect off a solar sail, impart mass to the solar sail, well, then they also, shouldn't they impart momentum to the laser projector as well?
Yes, they do.
Laser projectors on your ship, you could apply very small thrust with that.
Right.
You should also decelerate.
Yeah. Okay. So what he's saying is the laser that these ships carry can be used to provide thrust or impart thrust on another craft. Yes. So I'm assuming that these big convoy ships have massive lasers, massive supplies for dropping off the seed ships as they pass a new star. That same laser can be used for the final acceleration as you approach a supply ship that you're going to pick up. I forgot to mention, if you angle a light sail, you can get sideways force. But you get force both in the direction the photons are moving, but they reflect off, and so you get sideways force. So you might want to send an interstellar probe in another direction by angling it and sending it off, at an angle from your normal route, and so you can start exploring off to the sides. And yeah, it's a big problem of momentum conservation and energy management. So,
let's thank our speaker.
Okay, so that completes the technical part of our conference. Next, we're going to move up to the atrium. We'll take about a 10-minute break to move up to the atrium, and we'll start the hackathon. So once we get up there, let's move up there, and then we'll talk a little bit about how we're going to set it up and execute this. Once we get a little bit settled up, settled in there. Okay. Thank you, everyone.
I'll
Yeah, thank you.
Keep a cool head.
Not my first time under duress, you know, when you lecture for 10 years. You know what it's like.
Okay, I'm collecting stuff for tomorrow. By the way, I have misplaced my cell phone in case somebody
Oh my
turns in a
gosh, is
phone
that right?
to you. It should be somewhere here. Somebody will turn it to
Yeah,
you
what,
or you.
and you called obviously, and then you can.
Because it's on silent.
What kind of phone is it?
It's a Samsung.
Okay. Well, I'll
If somebody finds it,
tell
they will return it to you or maybe.
We'll have a look.
Do you guys send me the Andreas asked about if I is asking about no? Right, so he like as I was
No, that's why you want to take it with you. I want to take some time. That was nice.
The last presentation went better than the first one, definitely.
Oh, that was fun. So I think the better one is it.
You picked the one where it was more confident.
Well, I think where you have more confidence.
Yeah.
Actually, when you started the cell rack.
It's not, it isn't doing anything. I mean, it's research.
The list is fast. It's about.
Okay.
Except for any antenna.
Have you been seeing the thickness of 3.0 tethers?
No.
But I can say, micrometer, just there.
Okay.
I'm not sure.
You can't afford to make them any bigger?
No, because then the efficiency goes down. Mass to drag force ratio.
I'm actually kind of wanted to ask something I was actually about too, is stuff that you've done with the electromagnetic capacitors. You said you were actually absolutely out on their head. I think it's that capacitors have been done with everything in atmosphere. Exactly. That's the same thing. So, create the react at the same time. And here's the direct line, see, I'm just really interested in that concept now. That seems like it solves problems. Yeah. So, as you can use your computed engine to use your lighting, when you're ready to slow down, not only do you recapture or reduce your speed, but you can also use your power out. I think it's great.
Thank you for your help. I mean, you're a lifesaver being able to record this for us.
It's fine to leave the extension cords back there.
Trying to think. Yeah, we'll do these.
Okay. Also, we'll be shooting in here again, right?
Yes.
And will the setup be pretty much the same, a couple studios in the morning and the afternoon, and then another hackathon, or?
Exactly.
Okay.
Same exact setup, so hopefully it'll be a little bit more well-oiled tomorrow.
Yeah, are you guys not gonna do the live stream then? Or were you doing it on that webcam?
We were doing it on this one.
Okay, good, okay. So I can just bring the same setup for tomorrow?
Yes. Okay. Thank you.